Okay, off we go. So we do still have some examples I would like to have time to get to in Chapter 7. They're very supplemental. We have a backup plan in the form of the recordings that I can share with y'all. But hopefully we can have time to get to them. Amazingly, Chapter 4 goes super duper fast. It's largely mechanical. It's nowhere near as sophisticated as the Chapter 7 stuff. Nowhere near, not even close. In the interest of time and stuff, I am going to go pretty quickly through this Chapter 4 stuff. It, again, is largely mechanical. That's how we're going to get 3 sections plus done today. Picking up. 4.1 is really very short. Now, I know y'all remember this thing called the Taylor polynomial. Right? There's various different takes on what is it about the Taylor polynomial that's so interesting. And here's the take I'm going to give you. The Taylor polynomial is the unique polynomial of degree k that I'm going to say mimics the function f at the point a that we're interested in. So if you give me a point a, you give me a function f, and this is the best mimic among polynomials of degree k. So what I mean by mimic, I mean that it has the same value as f, it has the same derivative as f, it has the same second derivative, third derivative, etc., all the way up to and including the kth derivative. So pretty neat take on Taylor polynomials, I think. Obviously, if it's mimicking the function, then you would stand to reason, seem reasonable to guess that it would be a good approximation of the function. Okay. All right. It's the same in multivariable. Totally same idea. If you are, in fact, let me go full screen here. There we go. If you are looking at a particular function f at some point a in its domain, then you can talk about what is the unique polynomial of degree k that mimics that function. In the same senses, basically, it's going to have the same value, the same there's actually a bunch of derivatives. Okay, so all of the same partial derivatives, second derivatives, second partials, third partials, etc., all the way up to and including all of the kth order partials. So that's a lot. A lot of conditions to check. And in fact, it's kind of a lot just to write down what the formula is. It's in the book. It's notation heavy. So all we're going to have use for in this class is the degree 2 Taylor polynomial. And this is actually not that bad to write down. Here it is. Degree 2 Taylor polynomial. You're going to recognize right off the bat, by the way, that's just a linear approximation. The first 2 terms are literally the linear approximation for f. So all we're really doing is adding sort of a second order correction, you might say. Here it is. You'll even notice it looks kind of vaguely like what the single variable kind of looks like, and I didn't write it down. Anyway, y'all know what the single variable second order term is. It has a 1/2. It has 2 factors of x minus a because it's x minus a squared. Well, here it's not squared. Here it's just 2 different factors in different places. And then we've got this Hessian matrix, they call it, which is made up of all of the second partials at kind of playing the role of the second derivative, right? Where this is where the second derivative term would be if this were a single variable. So very analogous. It is different, though, very importantly different. Y'all may recognize this construction. It's called a quadratic form. Hope y'all might remember that from linear algebra class long ago. And so it's just the quadratic form for a given matrix, and the matrix is the matrix of second derivatives. So I would encourage y'all to do a quick check that this is true. that this is the function that approximates, that mimics f in the senses that we just listed. And do it. Okay, take pity on yourselves, right? Keep it low dimensional. Second order only, of course, right? But it's just a matter of kind of writing things down and checking that derivatives work the way that they sort of should. So anyway, all right. Everybody all right with that? We're done with section 4.1. Now, as always, when we go quickly through a section, do make sure to read through it. Make sure there's stuff that I don't talk about because I feel like you don't need my help on it, right? And again, we have to be super picky and choosy about what we spend class time on. Okay. All right. 4.2. So let's talk about extrema. Y'all know how to do single variable calculus. Y'all probably have seen at some point in the past that if a point, let's say this one, satisfies these three conditions, then there's absolutely no way that could possibly be a maximizer. The reason why is, and by the way, here's another point that satisfies those three conditions. They're in the interior, which means from that point you're free to go whichever direction might end up being necessary. The function's differentiable, so derivatives mean things. And if the derivative is non-zero, then look, the function is increasing one way or the other. Now it happens to be to the left for one of these points and to the right for the other one. But whatever, it doesn't matter which direction. The point is that the function is still in the process of getting bigger as you move legally through the domain. You're not at the maximum yet. I mean, so it's a pretty simple take. And here's the great news. The overwhelming majority of the points in most domains for most functions satisfy these conditions and therefore could not possibly be what we're looking for. Right? The only thing that could go wrong is one of these conditions might fail. Right? We might not be in the interior. We might be on a boundary point. And like you take this point on the left here, this point on the left, well, if I wanted to be based on what the slope appears to be, if I wanted to make the function actually get bigger to eliminate this as a possible maximizer, I would have to go out of the domain where I'm not allowed to go. Okay, so likewise for these other conditions, points where one of the conditions fails, at this point it's not differentiable. At this point the derivative is not non-zero. At this point the derivative is not non-zero. Handful of points that we can't eliminate. The overwhelming majority of points typically are eliminated. So now the reason I'm spending time mentioning single variable calculus is I want to make sure that everybody has a crisp understanding of how this works. It gets presented, I think, a little poorly in a lot of single variable calculus classes as take the derivative and set it equal to zero, and because when you're at the top, it should be kind of flat up there. I feel like it's a little bit lacking in what we're really doing. Most importantly, from a sort of philosophical point of view, what we are actively doing here is eliminating candidates. That's what we know. When I identify one of these points in the red, I know for sure that's not what I'm looking for. When I identify a point that's in the green, I don't know. All I can say about points in the green areas is that my argument fails, and I don't know, maybe it's what I'm looking for, maybe not. I throw up my hands, I have no idea. Right? And I think this is something that often gets miscommunicated in single variable calculus classes as that, when you take the derivative and set it equal to zero, you know something, and they give you this illusion of knowledge by giving it a name. It is a critical point. Critical point is code for we have no idea what's going on. Is that cool? All right. Okay. It's the same in multivariable. Same deal. Again, the great majority of points in the domain of most functions that you're ever going to experience are in the interior of the domain where the function's differentiable and the gradient's not 0. And at such a point, the function is still in the process of increasing and therefore could not possibly be a maximizer. I think it makes more sense like that. So again, a process of elimination that eliminates the overwhelming majority of the points. Now, okay, not every point. There are a small number of points maybe that don't quite satisfy. So there, the function fails to be differentiable. There would appear the gradient is the 0 vector. There, the gradient is the 0 vector. Ooh, also there. Handful of points there in the interior. And then actually a whole bunch of points that are on the boundary that simply fail to be in the interior in the first place. So all of these points are points where we can't eliminate. These are points where we throw up our hands in defeat. We have no idea what's actually going on at those points. Can't eliminate them, so we give them a label. We call them critical points so we can feel like we accomplished something. And really all we did is identify where we don't know what's going on. Is that cool? Real quick, I want to point out that there's more sort of interesting kinds of critical points in multivariable than in single variable. So for example, yes, there are maxes and yes, there are mins, but there's also saddle points like that and that, where it's, and there really is no single variable version of this, but it's concave up sort of in one direction, but it's concave down in the other direction. You can't have something like that in one dimension because it requires having two different directions to be able to talk about going. So this is a new concept. This is a new problem we've never faced before. There are these things called saddle points. And by the way, saddles are sort of the tip of the iceberg. I encourage you to do an image search for something called a monkey saddle. It's kind of like a saddle point, except it's got, instead of sort of two upward directions and two downward directions, it has sort of three upward and three downward. The monkey needs three downward directions, one being for his tail, right? So it's pretty cute. Somebody on one of the pictures I saw actually sort of, drew a little monkey on top of the thing. Okay, so let's put this into action. Here is a function. This is defined on all of R2, of course, because nothing explodes. Okay. And so, every point's in the interior, so we don't get any boundary critical points. This is a polynomial which is differentiable everywhere, so we don't get any, failure of differentiability critical points. So all we have left to find critical points is to compute the gradient, set it equal to 0, and solve. And in this case, it works out pretty easily to solve. Think it through, make sure you're good with that algebra, right? But these are the only 2 points that could possibly be what we're looking for. Now, how to identify what's going on there, and that's a different story. We'll talk about that in a bit. Okay. All right. Now, this algebra, from there to there, pretty straightforward. Not always so lucky, unfortunately. Sometimes you do have to worry about things. So, for example, if you want to solve this system, and I think you'll notice this pretty quickly, pretty immediate that x squared is equal to y squared. And a lot of high school algebra courses will tolerate or even encourage students to just immediately conclude that this means x equals y. It doesn't, right? look, I mean, if x were negative y, this equation totally works, right? So this is the kind of nonsense that, in some high school classes you can kind of get away with that, and the instructor will either studiously avoid any situations where that, creates a problem, or might not even be aware of the problem. You never know, right? So anyway, we can't do that. That's absolutely not going to fly for us. So we have to acknowledge the two possibilities, and each one is its own separate consideration, right? You got to check both possible cases. Now, these cases aren't hard. If x is equal to y, this remaining equation, well, you just plug in x equals y right into it and solve for y. That tells you x, boom. And then likewise, if x is negative y, well, just plug it in. Trivial algebra. Once you know y, you can back solve for x, because in this case too, x is negative y. Right? It's just a matter of accepting that we do have to deal with these two separate cases and just dealing with them. Is that cool? Say the word. If anybody a little weirded out by that, or everybody all right? Okay, so do we have a second derivative test? And, yes, we do. And it's not even that big of a surprise. It's a little weird, but it's not that big of a surprise, ultimately. Let's go back to single variable for a moment. Single variable, if you find a point where the derivative is equal to 0, this whole term goes away, and it all comes down, the behavior of the function near a, other than a constant, comes down to this one term. You just have to think through, well, how does this term behave? And it's entirely determined by this value of f double prime. Because 1/2 is always positive. This square is always, it's never negative. So you just look at f double prime, and f double prime is positive, then that means that these terms will all be positive, which means you're at a minimum. And likewise. Okay, so same deal down here in the multivariable case. If you find a point where all of the partials are 0, and thus that derivative matrix is 0, and thus this whole term goes away, then other than this constant, everything is going to be determined by what's happening, again, to the second order term. And, here's where things get a little weird. This is no longer just a simple scalar product of scalar factors, and you just count your pluses and minuses. This is a weirder thing because there's a dot product involved, and there's a matrix vector product. This is a non-trivial thing to understand, but again, we've already seen them before. Correction, y'all have already seen them before. It's a quadratic form. And y'all know already about this cool stuff about there exists such a thing as positive definite, and negative definite, and indefinite. Okay. All right. Well, this is a special case of all of that business, because this matrix, being made up of various partial derivatives, second partials, is symmetric. And y'all probably recall back in your linear algebra class that symmetric matrices have some really nice properties. In particular, they're all diagonalizable, right? And et cetera, all sorts of other good things. This is highly optional, so you don't have to do this. And even if you are interested, this is just hitting the highlights. There's a significant, and tricky is the wrong word, there's a kind of sophisticated, high-level linear algebra argument to be made here that gets us to the punchline we're interested in. You don't have to do it. But it does boil down to something that is easy to remember and serves as what we call the second derivative test. Now, this is for two variables. Functions of two variables. It gets weirder. when you have more than two variables. So you're only responsible in this class for functions of two variables. And the test is various cases. You got to look at this thing called the Hessian determinant, see if it's positive, negative, or zero, and then follow along and do what it says. And it's just a little flow chart. You just go through the flow chart, and it gives you a conclusion of some sort. Do notice, of course, one of the possibilities: if the determinant is zero, test fails, and we learn nothing other than the fact that test failed. Is that cool? Y'all probably remember there's something kind of like that with the single variable second derivative test. Okay, so let's walk through one. If I can get this thing to, okay, here we go. So we've already looked at this function. We've already found two critical points. Let's apply our second derivative test and just see what happens. We're going to classify these based on the second derivative test. Okay. We know we're going to need to know our Hessian determinants. Okay, great. So you take the Hessian, you compute the determinant, and here's what you end up with. There's your Hessian determinant. By the way, we may or may not also need fxx. Keep in mind that is the top left element of the Hessian matrix. So we've got everything we need. Now we play the game. And let's start with this point. At that point, let's see here. X is -1. And so our Hessian determinant is negative. And when the Hessian determinant is negative, that means saddle point. Let's play the game. Okay, let's look at the other one real quick. Let's look at this point, 1, 0. Well, again, with the 1, 0, I know X is 1. That means that my Hessian determinant this time is positive. That means, apparently I'm going to have to look at fxx. Fxx, again, keeping in mind we're looking at the point where x is 1. Fxx is 6, which is positive. And that implies local min. And again, game over. Is that cool? Everybody see how it works? It's a simple flow chart. You play the game, right? Compute the Hessian determinant. Make a note of which element in the Hessian is the xx second partial. Follow the flow chart. Okay. All right. Moving along. This whole section on global extrema is a longer conversation that we can really give a good treatment of. What I have here, I just kind of felt like, well, I should probably tell you all a couple of things about it. But when I wrote the notes, but time's short, and this is a luxury that we basically can't afford at this point. The short version is that there are some situations where there is no maximum, and that's always something to be worried about, right? So if you're playing a process of elimination game to try to find your absolute maximum, keep in mind that's what we do when we play optimization game. We take the derivative, set it equal to 0. We look for where certain conditions fail. And where the conditions fail is where we're like, we have no idea what's going on. So we are eliminating most of the points. We're looking at what remains. And then we're saying, whichever one of these has the biggest value must be the maximum. But if there is no maximum at all, then that's a bunch of nonsense. Right? So, for example, if you were to play that game with this first, and of course now my stylus dies. If you were to play this game with this function, well, there's a critical point there. There's a critical point there. This is the highest. of my 2 critical points. Does that make that the absolute maximum? Nope. The function's getting way bigger as you go that way. Right, so you do have to watch out for stuff like that, and okay, there's a whole thing about that. But I'm going to say not our problem. So I'm going to scratch. Y'all are not responsible for that. This is a tedious, blunt way of finding critical points on boundaries, and it's basically in there. I put this in the notes, not because it's a good plan. I put it in the notes so that we could laugh at it moments later when we see the much better method that's on the next page. Right? So let's just take a moment to be like, oh wow, look at that. It looks tedious. Look at all of the, oh my God, that's just a lot of effort. And we're going to just skip down to the much better method that, of course, everyone's going to use. This is the much better way to solve a problem like that. Okay, so that's 4.2. On to 4.3. So we're going to consider here a category of questions. And that is, we want to find either the biggest value or smallest value of a function. So we want to optimize one way or the other with an asterisk. And that is subject to a constraint. And that is, we're not allowed to just pick any point we want. The points that we allow satisfy some requirement, some what we call a constraint equation. So, for example, you want to find the point closest to the origin. So I want to minimize distance to the origin. Okay, well, the origin is the point closest to the origin. Seems like a simple question until you look at the constraint. No, the origin is not allowed. I want to note just among points satisfying that equation, which you see the origin does not satisfy, right? So the origin is inadmissible. It's not on the table. Now, of these points, which one is closest to the origin? And that becomes a much harder question. Does everybody see that? All right. Okay, so just to get some terminology established and see some examples, we need to always identify the function that we want to optimize. In this case, we're looking at distance to the origin. This is going to be called our objective function. And I know I just made a whoopsie, did it on purpose. It's a slick move. I like this little trick. If I find the point that minimizes distance squared, if you think about it, distance is always positive. So if I find the point that minimizes distance squared, that also minimizes distance. Right? Tricky move. But very convenient. Now I don't have to deal with square roots. So this is a good one to remember if you want to minimize or maximize distance. Don't use distance. Use distance squared. And avoid those pesky square roots. Does that make sense to everybody? Okay. All right. Now, what's my constraint? Well, my constraint is that this equation has to be satisfied, and what we're going to find to be extremely useful for the method that we're about to do is always view it as being a level set, right? And once we've rewritten our constraint as a level set, then whatever the function is whose level set you're looking at, that's what we're going to call the constraint function. So the equation itself is the constraint equation. When you write it as a level set, whatever function whose level set you're looking at, the function whose level set makes your constraint what we call a constraint function. Is that satisfactory? Yeah. So again, it's a choice, right? It's going to end up being a very convenient choice in just a moment. Okay, so this is a couple of big ideas. These are our two major players. two of our major players in the question. We're going to always have an objective function and a constraint function. And this is one of the things that makes this stuff a little confusing. There are, very importantly, two different functions, completely unrelated. Right? The thing that I want to maximize doesn't have to have anything at all to do with the requirement for the points I'm allowed to consider. Completely disconnected, unrelated functions. And they're both important. So do be careful about that. Now let's think through how this category of question comes up. Here is a pretty good example. Y'all have seen problems kind of like this before? Right, I'm going to find the biggest by volume box, rectangular box, with the requirement that it has a fixed given amount of area. Now, how would this come up? Well, maybe the area costs money, and you have a budget. You only can afford a certain amount of the material that it takes to make this box. So the area is settled, so you don't have any discussion of what the area of the box is going to be. But you could make it long and skinny, or tall and wide, or you can make it kind of generally cube-like, or you got all sorts of options there. You want to make the volume as big as possible. And in a situation like this, well, pretty easy to see. What we're trying to maximize is volume. So volume will be our objective function. And we have a fixed amount of area. So area is our constraint function. Everybody see how that works? All right, just another context, application type situation. This is more sort of like, small business economics, something along those lines. But if you have a limited budget, well, your limited budget is your constraint function, because the budget being limited means we're looking at a level set of that budget. So budget is the constraint. And what I want to maximize, productivity, so that'll be our objective. So again, a pretty natural, very real word, nothing abstruse about, where's my, here it is. Nothing abstruse about this example. You start a small business, you're going to have a limited budget. There's reality, ugly reality for you. And, of course, you want to, very often anyway, maximize your productivity. So, of course, you do. So, very natural question. Okay. All right. So, how to do it is, again, a process of elimination. We're basically going to steal the big idea that we talked about, 20 minutes ago for a single variable optimization, which is we identify some conditions, and if you're at a point that satisfies these conditions, let's think through what we have here. F and G are differentiable, just means that the derivatives and gradient vectors actually mean stuff. The gradient being non-zero, well, keep in mind what the constraint gradient is. By the way, notice that being the constraint gradient, it's the gradient of the constraint function. If it's non-zero, and keep in mind gradients always point perpendicular to their level sets, that means it defines literally the line perpendicular to your constraint set. By the way, that's where the level set thing kicks in. That's why we do it with level sets, so the gradient will be perpendicular. And then if the gradient of f is not a multiple, then that means that the gradient of f points off of the perpendicular. And this is why game over. Once we know that our objective gradient is pointing off of the perpendicular, then check out the following little computation I can do. It's off of the perpendicular, so it has a shadow. that is a velocity vector as I move through that constraint set. So I'm allowed to move in that direction, but I can't actually move in the direction of gradient f. That would take me off of our constraint set. But I can move in the direction of the shadow, and because we've established that that gradient is off of the perpendicular, I know that that's an acute angle. That means that dot product is positive. That means the function is increasing as I go this way. So, if the function's still increasing, right? In other words, because these conditions are satisfied, this point that we were thinking about could not possibly be a maximizer. And again, great news, the overwhelming majority of points in the domains of the overwhelming majority of functions that you're going to be interested in doing this kind of thing for, overwhelming majority will be eliminated. And all you have to worry about is the failures. Right? Where does this argument fail? And the argument fails where any one of those conditions fails. So we're going to sort of hide our failure by labeling them as critical points, trying to pass off a failure as a success. Right? And then we just have to deal with individually. Okay. All right. Okay, so that's the deal. And I've got 3 examples here I want to go through. There's some algebra to be done. I know y'all are good with algebra, right? So time being critical, I'm going to go right to the critical, bad choice of words, the most significant thoughts, right, relevant to these calculations. But y'all can go through the rest of the algebra on your own. Okay, so here we go. We're looking for the highest point. Okay, well that means we want to maximize that function. There's our objective function. Is that cool? We have a constraint. Now the constraint is already written as a level set. That's nice. And so my constraint function is like so. And so I just have to now go through my 3 conditions. I've got to check for where is there a failure of differentiability, where is the constraint gradient equal to 0, and where does this little weird equation happen. You just got to check those 3 things. You just go down the list. It's just a matter of doing it. And that'll give you all your critical points. We're going to go through that in just a moment. Does everybody see what the plan is? A little bit of terminology, just so we can talk about it. I like to call this the differentiability condition. I think it's pretty reasonable. It's hard to understand why I would use the following term, but there is a really good reason for this. I'm going to call this the degeneracy condition. And there's an excellent reason for this that's well beyond what we can talk about in this course, but that's the degeneracy condition. And this we call the Lagrange condition, because this is the main formula that I know most of the time where you're actually going to find your critical points most of the time. It's going to be from this one. So this lambda in here is just any scalar. Could be any scalar at all. It's called a multiplier. It's a scalar. I don't know why they have to call it a multiplier. But they use lambda because lambda starts with an L, as does Lagrange. And this is the Lagrange multiplier method. So Lagrange was the originator. And so, anyway, that's why I like to call this the Lagrange condition. Okay, so one at a time. Any failures of differentiability? Nope. That was easy. Right, these are polynomials. Polynomials are never have differentiability problems, so nothing to it. Now, before we go on, let's talk about the test. What do you need to do on the test? And here's the thing. remember we've talked about this before. This test is not about none of my tests. None of the tests in any math classes, right, are about answers. They're about demonstrating proficiency with important ideas and tools. Right? Well, let's talk about the tools here. We're going to make basically an elimination argument. And if you're going to make an elimination argument, you do in fact have to check all of the points. Right? So just as a dumb example, if I wanted to establish, who is the tallest person on Duke campus, is it good enough for me to just walk around the physics building and just be like, well, look at that guy. I think he's the tallest guy I've seen in the physics building. He's probably the tallest guy on campus. No! Nonsense. Right? So you do have to check all the points, which means you have to check all the conditions, right? If you don't check all the conditions, then you may just straight up be ignoring legitimate candidates that might have been the answer you're looking for, right? So not only do you have to show the process that led to what you're calling your answer, you have to make a mathematically valid argument, which means you have to check all the conditions, even if they don't give you critical points. Now, this is arguably a little bit uptight, right? But that's what we do here. That's what math is. And so it actually is kind of important. Now, here's the good news. Look how easy, right? In the great majority of cases you're going to deal with, both of these functions are going to be differentiable. So just say differentiable, boom, done, right? Your partial credit already, just right. You don't even have to fully write out the word differentiable, right? I would take diff. So it's a very small ask, right? But it is an appropriate doff of the cap to what I think is an important point. Okay, so make sure to do that. And again, reminder, it's part of how things are going to be graded. So you're leaving money on the table if you don't do that. So get your free money by writing that down. Okay, next we got to look for degeneracy. So we got to look for where the constraint gradient is 0. All right, well here's our constraint function. We take the gradient, we get this. I want to know where is that equal to 0. Well, a little bit of linear algebra will persuade you that that's equal to that. And then, of course, we want to know where that's equal to 0. You probably recognize these equations, again, from linear algebra. This is a little 3x3 system of equations. And you all have lots of methods for how to do those. And in this case, take the determinant. It's clearly non-zero. You got to work out the arithmetic. The determinant is non-zero, and we've got non-singular matrix. That means there's a pivot in every row, pivot in every column. That means that we have existence and uniqueness. And once you notice that 0 is an obvious solution, that means 0 is the only solution. Okay, so I hope that rings some bells. If that is something that maybe you're a little rusty on, come on into office hours. I'll be happy to help you polish off those skills. So very tempting to call this a degenerate critical point. Everybody cool with, okay. Now here's the thing. It's not. Critical points are points in the domain that we can't eliminate. Okay, the whole reason we're eliminating candidates is because they're in the domain, they might be what we're looking for, so we have to eliminate them. So, right, so this would be a failure to eliminate if it were in the domain, but it's not, right? So this doesn't satisfy the constraint equation. I don't need to be able to eliminate this point. This is not a failure to eliminate. This is wasn't on the table in the first place. And that's going to happen sometimes, right? So, I mean, just for this, extend the silly analogy, right? I mean, again, let's look for the tallest person on Duke campus. You don't have to worry about some guy you went to high school with back in Minnesota. He's not on Duke campus. He's not even eligible for consideration. Does that make sense? I have a silly analogy, right? But does everybody see what I'm talking about? This point was never allowed in the first place, so who cares? So not a critical point. Even better, it wasn't a candidate in the first place. Okay. Lastly, we write down the Lagrange condition, and the Lagrange condition is just a matter of writing down both gradients, setting them equal, setting one to be equal to a scalar multiple of the other, and so you have a little system of equations to solve here. Oh, wait. Again, we're only interested in such if they also satisfy our constraint equation. So in fact, we have a 4x4 nonlinear system, and these can get hairy. They can get very, very difficult to deal with. If it were linear algebra will crush it. It's not linear, right? So 4 equations and 4 unknowns, and good luck. Good luck solving. I'm going to show you a couple tricks. And I'm also going to point out that, well, by the way, I am not a monster. And I'm not going to give y'all an exam question where solving the resulting algebra is intractable, because that's just straight up not fair. Right? So the fact that these can be difficult to solve is mostly my problem, than more so than your problem, because I have to make sure that the question I ask is reasonably tractable. So this one, for example, is perfectly reasonable. And here's how it breaks down. Now I'm going to start by making a mistake, again, on purpose, dramatic purposes. I'm going to look at those two equations and consider, hey, wait a minute. Excuse me. Doesn't that mean these equations have to be true? I mean, you cancel the lambdas. Doesn't that mean these two equations have to be true? Tempting? This is the kind of, again, sort of stuff that, will pass muster in some high school math classes, and nonsense. It just doesn't work, right? So in particular, I mean, what's to stop lambda from being 0? And then these things here could be like, that could be a 7 and this could be a 9. What's to stop that, right? I mean, if lambda is 0, these things over here do not have to be 0. So just straight from here, concluding that they have to be 0, nonsense, right? Okay, so heads up for that. That's a dangerous whoopsie. Now, it's easily fixed, and it's fixed by looking at this equation. This equation does immediately tell us that, there's no way lambda could be 0. Right? 0 is not a factor of 1. Doesn't matter what you multiply by 0, you'll never get 1. So you gotta say that. You gotta write that down and establish that lambda is non-zero. Once you've established that lambda is non-zero, then this knowledge that is non-zero absolutely allows you to do that. Is that cool? Okay. All right. And it's kind of all over with the shouting at this point. Once you have these two equations, you can solve for x and y in terms of z, which you can plug into there, which then becomes this. And this is just a great big equation in z, which is pretty easy to solve for z. And once you know z, once you know z, that tells you your x's and y's that correspond. Everybody all right? Okay, so that's where the landmines are on this kind of algebra. By the way, big picture, this is a pretty good strategy to try to eliminate lambda. Look for opportunities to find relationships like we did here between x, y, and z that you can then plug into the constraint. That's this is a pretty good thing to aim for. That plugging into there, simplifying your equation. So you want to keep that in mind. A good tool for your toolbox on how to solve this kind of algebra. Okay. All right, let's look at the next one. Oh yeah, question.
Could you go over this? So in the matrix that we found, could we find the null space, and that would be just the zero vector?
Yeah. Mm-hmm. Oh, sure. Yeah. So if you basically just want to do the row reduction, you can. I think it's less work you can observe the determinants non-zero without writing much down. And so powerful tools will save effort, right? So I would encourage you to sort of think in those terms. But yeah, a row reduction becomes the exact same conclusion. Yep. All right. Okay, so here got another constrained optimization problem. So here's what we want to maximize. There's its gradient. Here is our constraint function, and there's its gradient. Notice the constraint function. We're looking at a level set of it. And we play the usual games. So condition 1, do we have a differentiability problem? Nope. Polynomials, boom. By the way, that's probably a free point. Think of that as a free point. Again, the glass is half empty take would be, you're going to count off a point for, not writing down something that was obvious. No, free point if you write down something obvious. This is a good thing. Take your free point. Right? Does that make sense to everybody? Okay, let's see here. Degeneracy. Where is this constraint gradient equal to 0? Well, again, easy algebra, even easier algebra in this case. You see x equals 0 is the only thing that solves the algebra, but it doesn't satisfy the constraint equation. So this represents my failure to be able to eliminate a point that I wasn't responsible for eliminating in the first place. So again, don't worry about it. This is not a critical point. It doesn't need to be. It was never a candidate in the first place. Okay. All right, and then back to, you write down the Lagrange condition, and again we have to solve, and how do we solve this system? And again, tempting, but there is a landmine, tempting to solve for lambda in both of these equations. And if both of these things are equal to lambda, then they must equal to each other. Very tempting. And that's another good general move, by the way, and I encourage you to, should be a tool in your toolboxes. Solve for lambda in all of your equations. Those things must all be equal to each other. The problem, solve for lambda, I have to divide by x in the top equation, I have to divide by y in the bottom equation, and you can't just go around dividing by stuff unless you know it's not 0. So, it's annoying, but you gotta do it. And good news, it's pretty easy to eliminate the possibility of x and y being 0, because if you just plug in either x or y being 0, the equations don't work. You get 1 equals 0. So, it's no trouble. Whenever you're going to divide by something, you better make sure it's not 0. You better make sure that you know that it can't be 0. Otherwise, your algebra's got a problem. And then again, here we have a relationship between x and y, and you can plug that into here, and even better, you can first do this, then you take that and plug it into there and solve, and again you get y, and again once you know y, missed that wrong tool. Once you know y, you also know x. So, I mean, the details. Y'all are good at algebra, right? But I just wanted to point out the sticky wickets there. Yeah.
Could we do all this with the Lagrangian? Like, by setting it up?
With the what now?
The Lagrangian.
The Lagrangian.
Like, f of x, y, like, minus lambda times the constraint. And then you...
I don't know what you're talking about. I'm sorry.
I'll talk to you now.
Yeah. That'd be fine. Yeah. Okay. Okay. So, okay. Last example. And this one's really the most impressive one, I think. So now again, details to be dealt with. You identify the functions. They're both differentiable. That's easy. You look for possible degeneracies. None. So no problem. Again, you got to write this down. This didn't result in any actual critical points, but that's good. I mean, this is important reasoning, and you got to actually do that. Otherwise, your other reasoning doesn't mean anything, basically. And so how do we deal with this algebra? And now, I'll tell you what a lot of people do. A lot of people mess this up pretty badly. Very, very tempting. But a lot of people will look at this first equation and say, well, the first equation means lambda has to equal to 1, doesn't it? And this second equation means lambda has to equal to a fourth. And this third equation means that lambda has to equal to a 9. How could lambda equal to these three different numbers? No solutions. Y'all see the temptation there, probably, right? And again, I'm playing too fast and loose with zeros, right? You can only conclude that this lambda has to equal to 1 if x is not 0. If x is 0, that lambda could be anything. And likewise with the others, right? So if you're careful here, you got to break it down into cases, right? I mean, we know all of the variables x, y, and z can't be 0. If they were all 0, it wouldn't satisfy our constraint. Oh gosh, wouldn't satisfy our constraint. So that means at least one of them has to be non-zero. And you just break it down into these three cases. So, for example, if x is non-zero, then yes, indeed, lambda has to equal to 1. If lambda is equal to 1, that would mean that y and z have to be 0. And if y and z are 0, that would mean x would be plus or minus 6. So we got a little three-step process there, right? But in consideration, as long as x is not 0, then yeah, we've got these two possible acceptable results. And you can play that same game for the others. You can do the same for the, if y is non-zero, yada, 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 there's these possibilities, and if z is non-zero, yada, 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 very analogous. These possibilities, and check it out, that gives us actually 6 critical points. So this is one of the reasons, I mean, aside from mathematical completeness, right, this is one of the reasons I think worrying about, don't play too fast and loose with your zeros, and the legality of your algebra. If we had played fast and loose here, we would have walked away and missed 6 critical points. And even from a practical, turn the crank, get the answer point of view, you got to admit that's pretty unacceptable. Right? Is everybody happy with that? Okay, so that's chapter 4. And so now we have, let's say about 10 minutes to go through and talk about these 6 examples. I'm not going to do them quite, let's see, let me do them in the, which one do I want to do? I guess I'll just do them in order. Okay, so some things to keep in mind. Just general strategy for computing line integrals and surface integrals. Let the diagram do some work for you. I mean, it's very helpful, right? So identify what you've been asked, identify where that is on the diagram, and that eliminates some possibilities for one thing right away, and tells you some things to try. And it's a source of ideas. It's a source of, it even tells you specifically something you should compute. Right? So compute what it tells you to compute. Think about the boundary considerations, and that might alone give you a way to solve the problem. And then every so often something cool will happen. So always head on a swivel and think about stuff like that. Always be on the lookout for symmetry and fortunate geometry and stuff like that. Okay, so for example, here's a question. It says compute a line integral. By the way, I noticed that this vector field has 3 coordinates. I noticed that my parametric curve has 3 coordinates. I even notice, not that this is the deal breaker, but there are x, y, and z in these expressions, which means there's at least 3 dimensions to be worried about. Could be more as far as the variables are concerned, right? I mean, not all variables actually have to show up, but the fact that there are 3 coordinates in the vector field and 3 coordinates for your parameterization means we're in 3 dimensions. Is that cool? So we're looking for a line integral in 3 dimensions, and there it is. R3 diagram, that's where the line integral is. And right off the bat, there's some great information, 3 information that the diagram tells us. I should look at my vector field and compute its curl. It's just telling us to do it. I should also think about whatever my curve is. I should ask, hey, what are the boundary points of that curve? Because one way or the other, that may help us resolve the question of whether this curve has an anti-boundary surface, which would also be useful. Now here's another thing that we know. We know that these are the only 2 accumulation theorems, density theorems, boundary, whatever you like to call them. These are the only 2 that relate to line integrals. And so again, helpful free information. The diagram is telling you. Don't write down divergence anywhere on the page. Please, it's a bad look. It makes it look like you're guessing. Right? And you got to keep in mind, whenever we grade exam papers, we're trying to get some confidence about what you understand. Right? And so we are aware of the strategy that I like to call shotgun style problem solving, which is to just write down everything that might get everything you possibly know, and if any of that might conceivably be relevant, and you're hoping for partial credit. Yeah, again, and I know a lot of high school classes encourage that, and I think maybe the AP exam encourages that, but that doesn't really make any sense. Try that in any other class. Try that in a history paper. Or you just write down everything that might possibly... No, you have to have a coherent theme. You have to make a point, right? So, it's not helpful, right? So, again, the diagram will protect you against stuff like this. Identify where is the thing you've been asked to compute. And stuff like divergence or triple integral, right? Got nothing to do with, don't say Gauss, right? Gauss's theorem, there's no way that could possibly be relevant here. So just don't write it down at all. Is that cool? Everybody see what I'm talking about? Okay. So lots of free information, right? We're going to think about endpoints. We're going to compute the curl, and we're going to studiously avoid triple integrals, divergence, and the word Gauss. And with all of that helpful information, let's now go back to here, and let's think about the endpoints first. Our parameterized curve here starts at, let's see, let's plug in t equals 0, and I get 0, 1, 1. And then our curve ends at -1. I don't really care about the rest. These are clearly different points. Once you know they're clearly different points. Did I do that arithmetic right? So cosine of pi is, yeah. So these are clearly different points. That means that our curve has one starting point. It has a different ending point. And so this curve has to look something kind of like that. And apparently does not enclose any area. This is not a boundary. Is that cool? It's not a boundary, so there is no anti-boundary. So back to the diagram. I got a boundary there. So there is no anti-boundary surface. That means Stokes' theorem off the table. Is that cool? I mean, I hope y'all are noticing that. I mean, the diagram it's got everything is organized on it, and it just methodically has eliminated, two of our three big theorems that we might conceivably, have been able to use, and now there's really only one candidate remaining. Okay, all right. The next thing I'm supposed to do, I'm supposed to compute the curl of my vector field. So, okay, let's compute that curl. And here we go, computing the curl. Okay, well, let's see here. Oh, gosh. By the way, my little hack I know that the little partials are going to go like this. And I know that there's sort of I, J, K up there. And so I don't know. This is how I like to think. So when we're looking for the first coordinate, we're going to take the Y partial of that minus the Z partial of that. Eventually you'll just kind of use your imagination and sort of see those things up there. But I like to, anyway, sometimes you might want to write them down. So let's see here. The Y partial there is 1. The Z partial is 1, so that gives me a 0. Let's see, next I'm going to have the Z partial of the first coordinate is 2x minus, and now the X partial of that is 2x. So that difference is 0. And then lastly, the X partial of that is 2y. And the Y partial of that's 2y. Okay, so we have computed the curl. The curl is 0. Back to the diagram. We computed the curl. We got 0. That means there is an anti-gradient function. That means fundamental theorem of line integrals is on the table and almost certainly the best way to solve this problem. Is that cool? Everybody see what I did there? So now I went through that slowly and tediously, and you might be thinking to yourself, okay, well that was an awful lot of trouble. But I was going slowly just to be, as clear as possible. In practice, most of the time, you'll do a sizable amount of this, kind of just boom, 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 right? Once you see what the diagram's telling you to do, it's just boom, boom. This is a 30-second process, not a 5-minute process. That make sense? Okay. All right. Now, gosh, we have 5 minutes left, and I am supposed to leave 5 minutes for doing course evals. So I think we're going to have to stop here, but the big point my big goal with these examples anyway was to illustrate how to use the diagram and how the diagram will guide you and give you hints and eliminate possibilities. And I think we did that pretty well with this example. So I'm going to give you the uploads of the videos that I have that will go through the rest of the examples in great detail. Hope you'll find those useful. And we'll call it a course there. Okay, so y'all got your electronics. The evals are on Duke Hub. I'm sure y'all know better than I how to access them. So go ahead and I will hang out for 5 minutes.